Hello, everyone. Today we are going to learn about the properties and images of tangent functions. Today we are going to study tangent function, so let's review what is tangent function. We already know that for any angle x, x is not equal to half pi plus k pi, k belongs to z, and there is a unique tangent x corresponding to it. So y equals tangent x is a function, which we call tangent function. So how do we study the properties and images of the correct function? First, let's review the process of studying sine function and cosine function. When studying sine function, we first get the image of sine function by defining an unit circle. Sine curve. Its properties are studied intuitively through images. When studying the cosine function, we translate the sine curve to get the cosine curve, and then study its properties. Obviously, the image of tangent function cannot be obtained by translation, but with the previous learning experience, we can change the angle. That is, starting from the definition of tangent function, we first study some of its properties, help us study the image of function through properties, and then study other properties. So today we will study the tangent function in this way. First, let's look at the properties of tangent functions. So, when it comes to studying the properties of functions, what do you think of first? I think someone's answer will be the definition field of the function. The definition domain is the largest scope of a function we study. So what is the definition domain of tangent function? From the definition of the tangent function, we know that the final edge of the angle cannot fall on the y-axis. Therefore, the definition domain of tangent function should be a set of all real numbers that are not equal to half pi plus k pi, and k belongs to z. In this form, we remove all values that cannot be obtained from the set of real numbers. Are there any other representations? We can also express all available values in the form of intervals, that is, from negative half pi plus k pi to half pi plus k pi, and k belongs to the open interval of z. In this form, each determined k value corresponds to a specific interval. For example, when k equals 0, it corresponds to the open interval from negative half pi to half pi. When k equals 1, it corresponds to the pi interval from half pi to 3/3 of pi. When k equals negative 1, it corresponds to the interval from negative 3/3 of pi to negative half pi. Then the definition domain of tangent function should be the union of these infinite intervals. Okay, we have made clear the different expressions of the definition domain of tangent function. So what characteristics should the image of tangent function have? The image of the tangent function should be divided by an infinite number of lines x perpendicular to the x-axis equal to half pi plus k pi, k belongs to z, and part of the image between the two lines should be continuous. Let's look at the parity of functions. The definition domain of the tangent function is symmetric about the origin. Then from the induction formula we have learned, we can get the following conclusion. Tangent negative x is equal to negative tangent x for every value of the domain. So the tangent function is an odd function. So what are the characteristics of the image of odd function? The image of an odd function should be symmetrical about the origin. We already know that sine function and cosine function are both periodic functions, so does the tangent function also have periodicity? Similarly, we can get relevant conclusions according to the induction formula. Tangent x plus pi equals that tangent x holds for any value in the domain. So the tangent function is also a periodic function, and pi is one of its periods. So we study the definition domain, periodicity and parity of tangent function. So what kind of help will these properties have for us to study the image of tangent function? Since the current function is a periodic function, we only need to draw its image in one cycle, and then translate the image to get the image in the whole definition domain. So which interval with length pi should we choose? We can choose the interval from negative half pi to half pi. Because of the parity of the function, we only need to draw the image with y equals 3x in the range of 0 to half pi, then we can get the drawing path of the tangent function image by going back in reverse according to the analysis we just made. First, we symmetrize the image from 0 to half pi about the origin. You get the image of the interval from negative half pi to half pi. Then shift the image to the left and right, and each time shift the unit of pi, you can get the image within the entire definition domain of the correct function. Now, let's first study how to draw an image where y equals t and x are between 0 and half pi. We can draw the picture by tracing points. In order to describe the point coordinates more accurately, we can use the unit circle to find the geometric meaning corresponding to the tangent value. We make the angle x from 0 to half pi in the rectangular coordinate system, where the intersection of the edge and the unit circle is point B, and the coordinates are set to x0, y0. We make a vertical line through the x-axis in direction B with the vertical foot M. Then we make the middle of the vertical line and the angle of the x-axis at point 1, 0, and meet at T. From the definition of the tangent function, we know that tangent x can be expressed as the vertical coordinate y0 of point B is greater than the horizontal coordinate x0. Then it can be transformed into that the length of line MD is longer than that of the upper line OM, which is equal to that of line AT is longer than that of the upper line OA. Since the length of OA is 1, the length of line segment AT can represent the tangent value of angle x. Through the line segment AT, we can draw points. Let's look at the specific process. From 0 to half pi, let's take the 4 equal points. 8 pi, for pi, 3/8 of pi. In the unit circle, we divide the angle from 0 to half pi by 4 and find the line segment corresponding to the tangent value. By translating the line segment, we can find the ordinate of the corresponding angle. Of course, if we want to draw more accurately, we can take more points. Let's connect the obtained points with smooth curves, so we get the image of the tangent function from 0 to half pi. Next, we make this image symmetrical about the origin to get the image of negative half pi to 0, and then we get the function image of the period from negative half pi to positive half pi. Then translate the image to the left and right, and we can get the image of the tangent function in the definition domain. The image of the tangent function is called the tangent curve. We get the image of the tangent function, so we can more intuitively study the properties of the function. First, let's look at the monotonicity of tangent functions. From the tangent image, we can know that the tangent function is monotonically increasing in the open interval from negative half pi to half pi. From the periodicity of the function, we can conclude that the tangent function is monotonically increasing in every open interval from negative half pi plus k pi to half pi plus k pi, and k belongs to z. Please pay attention here. First, since the endpoint of the interval is not within the definition domain of the tangent function, the monotonic interval of the tangent function must be written in the form of an open interval. Second, we emphasize that the tangent function in each interval increases monotonically. Then in this form, any value of k corresponds to a specific increasing interval. As we mentioned earlier, the domain of a tangent function is the union of these infinite intervals, so the tangent function does not have monotonicity in its entire domain. Let's look at the range of these functions. When x belongs to negative half pi to positive half pi, they can take any real value from negative infinity to positive infinity, but there are no maximum and minimum values. Therefore, the range of the tangent function is the set of all real numbers R. Now let's look at the properties of the tangent curve, the asymptote. As we know, the image of tangent function is an image composed of infinitely many sets of curves with exactly the same shape separated by infinitely many parallel lines. Then when x approaches half pi plus k pi, and k belongs to z, the function value approaches positive infinity or negative infinity. So x is equal to half pi plus k pi, and k belongs to z and is the asymptote of the function. Is the tangent curve symmetrical? First of all, we have to consider the tangent curve. Does it have a center of symmetry? Since the tangent function is an odd function, it is not difficult to find that the tangent function should be a centrosymmetric figure, and the coordinate origin is its symmetrical center. Besides, are there any other centers of symmetry? The intersection k pi, 0 of the function and the x-axis is the symmetry center of the function. In addition, half pi plus k pi at the intersection of the indirect line of the function and the x-axis, 0 is also the symmetry center of the function. So the center of symmetry of these functions is half k pi, 0, and k belongs to z. Please pay attention here. The symmetry center of the tangent function includes not only the intersection of the image and the x-axis, but also the intersection of the asymptotic line and the x-axis. That is to say, the symmetry center of the function is not necessarily on the function image. For example, we are familiar with the inverse scale function. The origin is its symmetry center, but the origin is not on the image of the inverse scale function. Through the tangent curve, it is not difficult to find that the tangent curve has no axis of symmetry. Finally, let's look at the 0 point of the function. The 0 point of a function refers to the value of the real number x for which the value of the function is 0. It is not difficult to find the point of the function from the tangent curve because k pi and k belong to z. Above, we intuitively enrich the properties of the tangent function through the image of the tangent function. Next, we solve some problems through the function properties and image. Let's take example 1. Without evaluation, the tangent values of the following groups were compared. We can compare the value of the function through the monotonicity of the function. When the angle is not within the same monotonic interval, we can convert these values through the period. Let's start with group 1. Tangent negative 1/5 of pi and tangent negative 3/7 of pi. Since the negative half pi is less than the negative 3/7 of pi and less than 0, and the correct function is monotonically increasing in the open interval from negative half pi to 0, the 1/5 of pi with negative pi is greater than the 3/7 of pi with negative pi. Let's look at the second group. Tangent negative 13/4 of pi and tangent negative 19/5 of pi. These two function values can be converted first through the cycle. The tangent negative 13/4 of pi is equal to the tangent negative 13/4 of pi plus 3 pi is equal to the tangent negative 1/4 of pi. Similarly, the tangent negative 19/5 of pi can be converted to tangent 1/5 of pi. Since negative half pi is less than negative 1/4 pi, less than 1/5 of pi, and less than half pi, the function is monotonically increasing in the open interval from negative half pi to positive half pi. So the tangent negative 1/4 of pi is less than the tangent 1/5 of pi. That is, the tangent negative 13/4 of pi is less than the negative tangent 19/5 of pi. So we can compare the size relationship of the two tangent values. In the process of solving similar problems, please note that the requirement of this question is to compare the magnitude relationship of tangent values without evaluation. We can compare the tangent value as two function values of the tangent function, which requires placing the angle within the same monotonic interval. When the angle is within the same monotonic interval, we can directly compare, but when the angle is not within the same monotonic interval, we need to adjust the angle to the same monotonic interval through a period or induction formula before comparing. Now let's take a look at example 2. Find the domain, period, and monotonic interval of function y equal to tangent half pi x plus 1/3 pi. By utilizing the properties of tangent functions and algebraic transformations, we can obtain corresponding conclusions. Here, we can consider half pi x plus 1/3 pi as a whole and obtain the relevant properties of this function through the properties of the tangent function. So, the idea of such substitution is often used in our handling of related function problems. Let's first take a look at the definition. Half pi x plus 1/3 pi is considered as a whole, and its value cannot be equal to half pi plus k pi. K belongs to z. The range of x can be solved as x is not equal to 1/3 plus to k, and k belongs to z. Therefore, the domain of the function is the set of all real numbers that are not equal to 1/3 plus to k, and k belongs to z. Let's take a look at the period of the function. Consider half pi x plus 1/3 pi as a whole, denoted by z, since adding pi to reagent z equals reagent z. Adding pi to the sum of half pi x plus 1/3 of pi equals half pi x plus 1/3 of pi. The sum of x multiplied by half pi and 1/3 pi is equal to the sum of half pi x and 1/3 pi. The above equation holds for all values within the domain, therefore the period of the tangent function is 2. Finally, let's take a look at the monotonicity of functions. Add 1/3 of pi to half pi x and place it in the range where the solution x is greater than negative half pi plus k pi, less than half pi plus k pi, and within the range where x is greater than negative 5/3 plus 2k, and less than 1/3 plus 2k. Therefore, the monotonically increasing interval of this function is from the negative 5/3 plus 2k to the 1/3 plus 2kk, which belongs to the open interval of z. Okay, that's how we solved the problem. I will summarize the content of this lesson below. In this lesson, we obtained some properties of functions through the definition of tangent functions, induction formulas, etc. Furthermore, we were guided by the properties to create a graph of the tangent function. Reusing images helps us discover more properties and helps us understand them. And we have solved the relevant problems using properties and images. Okay, that's all we learned in this lesson. Thank you for watching. Goodbye.